just showed everybody my laser pointer. It looks like this. Can you see it? I put a little, you can't see it, can you? I'm just going to make it blurry here. See? There's a little red wire I taped on there. Can you see it now? Maybe it's not blurry now. Might still be a little blurry. What if I do this? Will it focus on my hand better? Not really. Anyway, I got a little red wire taped in there, and it's making a thing. I'm going to point it over there with it still pointed vertical like this. I'm going to do that from the back of the room, so you may, there may be a small delay here. And I'm going to turn the lights out, right? Alright, so let's see what my laser pointer does when I point it up there. So, if you are looking at my computer monitor, can you see the laser?
Yes.
You're nodding, good. Yes, this is a, yeah, so I've got it pointed vertically. You can see this wire here is causing some little lines. So you might think, if you just look at that, you might think that it might just look like, you know, two little lines up there because it's got a wire and the two spaces on either side of the wire where the light's going to come out. What we're seeing here is, I wonder if the camera can hear me okay. What we're seeing here is light spots and dark spots because of wave interference. So just like that study.com sound video we watched talking about sound attenuation, where you have a loud spot and quiet spots in auditorium because of the sound waves are doing constructive interference and destructive interference. That's what's happening here. The light waves are doing constructive interference and destructive interference. This goes with that one of those light videos that we watched too, and the one where it talks about the double slit experiment. That's what this is. That light is coming out the two slits on either side of this red wire and making this interference pattern visible. This is wave interference. Technically, diffraction is also happening because light is passing through a narrow opening, and the diffraction part is this light is spreading out way on that side and way on this side, and wave interference is also happening. So the light's spreading out because of diffraction, and we got wave interference. That's pretty cool. Huh, I guess that stuff was kind of bright over there from that window, whatever. I'm going to take the battery out of my laser for safety. And now we're ready to do lens stuff. Well, we will be in a minute. I'm turning the light back on. There's a couple of things. Turn the light on. Here we go. Light. There's a couple of things I want to go over before we start. Little things about light. For those of y'all that got to watch the circular polarization video, which isn't everybody, but that guy talked about what light actually is, and it's kind of hard to understand. I don't completely understand it myself, but light is, it's called an electromagnetic wave, and the reason it's called an electromagnetic wave is because that's what it is. Light is electricity and magnetism in one. So there's an electric field that goes this way. Are y'all looking? Electric field goes this way, horizontally, or whatever. And this is kind of a simplification of what it actually is, from what I understand. So there's an electric field, and there's a magnetic field going perpendicular-wise to it. Well, they're both going in the same direction, but they're perpendicularly oriented, perpendicular planes. That's what light is. And I don't completely understand why that results in light, but it's a whole quantum thing with the photons and everything. So that's quantum stuff is hard to understand. those waves, electromagnetic waves, can travel through a vacuum. Like the sun has to go through space to get to us. There's no stuff in space. I mean, maybe there's a little bit of stuff, but like we can see the stars that go through areas where there is nothing, no atoms for miles and miles, kilometers and kilometers in astronomy speak. They don't talk about miles. But that's one of the main differences between sound waves and light waves. Y'all know, you've heard that there's not supposed to be sound in space. That like if there's an explosion in space in a movie and it goes like it's not supposed to be that loud because there's not that many atoms in space. Now you might hear something if it's like in Earth orbit because our atmosphere, you know, has little bits of atoms out there. Like there's atoms out there. You know, you get higher up in our atmosphere and outside the area that planes can fly and all that. The air is not very dense at all, but there's air. So you might hear some sound, just not very much. The denser the air is, the better sound travels. Have y'all ever noticed that you can hear things more betterly when it's really cold? Anybody? Yeah, you go outside and you can hear better through the air. I think I've noticed that, and it makes sense to me because cold air is denser than hot air. Now maybe I'm just thinking that because when it's hot, there's lots of bugs and they're making noise, and when it's cold, everything is hibernating and stuff, and there's not a lot of noise, so every little noise you can hear. But it really sounds different. I feel like just like underwater, sound travels better, faster through things that are denser. Anyway, in space, where there's not very many atoms, or if there's no atoms, sound will travel not very well or not at all. And that's the difference between mechanical waves and light waves. Like, what was it? Sound waves and seismic waves into Earth and water waves, those are all examples of mechanical waves. Those all need atoms to travel. They won't be able to transmit they won't be able to move energy from one place to the other without that matter that's going through. You remember in Bill Nye's video where he had the pool balls lined up? Those pool balls are what transferred the energy. The pool balls themselves didn't move very much. When one hit the next one hit the next one hit the next one. It was a whole chain reaction. They all moved like an edge, but what they moved was that kinetic energy that was transferring from the pool ball to the pool ball. That's how my vocal cords are working. They're hitting the air hits the next molecule all the way to your ear. The molecules aren't really moving that much. It's this kinetic energy that my voice is making. So that's one of the main differences between, that's one of the most important differences between electromagnetic waves, don't need a medium to travel through, can travel through a vacuum, which means it's space, there's nothing, and mechanical waves, which need a medium to travel through. What else? Right. We kind of talked about this when excuse me. We kind of talked about this when we were doing that color thing, light and color. How white pigment, you start with white pigment, and the more pigment you add, eventually if you add enough pigments, you'll get black color pigment. If you shine like a red light on that black color pigment, what color is that black color pigment going to look? Imagine that it's like not shining at all. It's not going to look red. If you shine the red light on the white page, that page is totally going to look red. Or a blue light, that's totally going to look blue. Green light, totally going to look green. The difference between white pigment and black pigment is white reflects all light. That's why it's white, because you put all the light together. You turn the red on and the green on and the blue on. They make white when they're mixed with each other. So a white paper is reflecting all those wavelengths. That's why it's white. A black piece of paper, if you shine red on it or green or blue, it's not really going to change color. You shine all of them at the same time, it's not really going to change color depending on how shiny it is. If you have a perfect matte black, like there's a, I wonder if I can show it. Yeah, they painted that BMW in Vanta black, and you can't really tell. You can't really see like the curves of the BMW. They did it like for art. It was very expensive because there's a guy that holds a patent on that color, which is not very artsy of him. But I think it's a guy.
Wasn't he the guy that made the bean?
Made what?
A bean.
I don't know.
People just call it the bean because they don't respect the guy.
Anyway. Excuse me. Speaking of black cars, we got a loaner car that was black, and it had black seats and a black exterior. Are y'all listening? Yes. That car absorbed all wavelengths of light. What do black cars do? What does anything black do with the wavelengths of light that they absorb? They turn it into heat. They don't reflect that light. It doesn't come out of that material. It stays in there. That light is converted to heat. We got in that black car and tried to like touch the controls, and I burned my finger. It's not cool. And I was thinking, man, okay, when this kid gets his license in December, we're gonna see if we can get him a used cheap car, a good car, and whatever we can find. And now I'm thinking like, no, I'm not getting him a black car because it's we live in Texas. It gets too hot to have a black car, in my opinion. Now, if you want to do that for style, and you want to make a decision that considers all the facts, you value your style more than the temperature that car is going to absorb, and you do what you want. But the point is, the color black absorbs all wavelengths, turns it into heat. Color white reflects all wavelengths, and you get less heat that way. So it can be useful to consider that when you make a decision about what color to wear and all that. Unless it's felt season. All right, what am I doing now? I'm going to show you all about the waves. Where are we? No, not those waves. All right, we've done two labs recently. One I called Refraction Lab. That is the PhET, the online Colorado.edu thing. We had a laser on the internet, and you could click on it and point it different ways and change the color and point it into prisms. That is called Refraction Lab, that PhET thing. We didn't do it on the 13th, but we did it on the 8th, I think is what it was. But there wasn't 5 days for you all to make up the assignment if you missed it in between the 8th and the end of the 6 weeks. So I had to put it on this 6 weeks, and that's why the date is weird. So that's the Refraction Lab. The lab that we did with mirrors and lenses, that's the Mirrors and Lenses Lab. The assignment we're doing today, we're drawing ray diagrams with lenses and mirrors. This assignment is called Ray Diagrams, Lenses and Mirrors. So be careful, those names might be easy to mix up. I tried to make them as different as I thought I could. Anyway, long story short, too late. Let's do a ray diagram. So I'll show you one of these with the converging lens. It's not a convex lens, even though both sides are convex. That's not the way we refer to lenses. This is a converging lens. A lens that is concave on both sides, we'll call that a diverging lens. But, all right. So just like before, all the ray diagrams start from the top of the object, and just like before, the first ray diagram goes parallel from the top of the object, parallel to the principal axis to the lens. So this is a lens now. We did mirrors before, so these are actually going to go through when they go through. And because it's a lens, refraction happens, and that's why the lens changes the direction of the ray. So the mirror did it just by being curved. The lens does it with refraction, and part of that is due to the lens's shape, because the different shapes of lens make different refraction. But when this goes in, it'll actually bend, it'll slow down, and then when it comes out, it's going from glass or whatever this is into air, and it'll change direction again. I'm not going to draw it doing that because I just want to show y'all how to draw a good ray diagram with the lens. So what I'm going to do with each of my rays is go to the center of the lens and then refract or do whatever it says. So first one says parallel to the principal axis to the lens. We did that. And then refracted through the focus on the opposite side of the lens from the object. Yeah, it's a lens now, so we can go. Oh, okay. This is a straightish line. I think that'll be fine. You need to be careful to draw your arrows long enough so that they intersect with the other parts, just in case. Here we go. Okay. Number 2. Through the point where the center of the lens meets the principal axis, this ray does not refract. So this one will just be a straight line, it doesn't bend. Where the center of the lens meets the principal axis. No, that's not where the ray goes. Okay, okay. Okay. All right. And those are my 2 rays. That's ray number 1. Is that a 1 really? Okay. And this is ray number 2. Step 3 is just like before. Draw an arrow to show where the image will form. Top of the arrow, top of the object goes on, I guess this is the top of the image. Top of the image goes where they appear to intersect, and the bottom of the image goes on the principal axis, and that's my 3rd step. And all that's fine. I hope this is getting a little easier. We did this the day before today, and we did this on that lab. So hopefully it's getting a little easier, especially when there's only 2 lines to draw. We're adding something this time. So we're going to choose between 2 words 3 different times to describe the image. So the first thing is upright or inverted. This is probably the most complicated one to choose from because let's say that this object was down here at first and we had to draw from here. If this was upside down and it still ends upside down, we would choose upright because it did not get turned upside down. Because it was upside down first, it did not get inverted, so it's upright. It's not about where it ends, like just because it ends upside down doesn't mean it's inverted. It's about that it was right side up, it got turned upside down, so it did get inverted. And that's why we'll choose those. Magnified or reduced, this can also be a hard choice because sometimes you can't tell. It's not that big a deal. If you can't really tell, you don't need to go measure real carefully or anything. Just pick one, it's fine. I just want you to know, I just want to see that you know what these words mean. This is smaller than this one, pretty sure, so I'm going to say this was magnified. Some of them will be real close, and those you can just pick one because it doesn't matter, it's fine. I just want you to know what those words mean. And this image is real because these rays actually go there. When we used the dotting lines before, those are going to be virtual, and we'll see that when we get to the new kind of lens. And I'll come back and show you all the diverging lens, where hopefully we'll get a virtual image in it. Okay. So here's the diverging lens. The first ray, what is that? The first ray is just the same, parallel to the principal axis to the lens, but then it refracts differently. So, parallel to the principal axis to the lens, and then refracted on a line as though it had already gone through the focus on the same side of the lens as the object. So let me show you what that means, because it can be a little weird to interpret. As though it had already gone through this focus means like that. It points directly away from that focus, kind of like with the convex mirrors. Points directly away from that. Like the convex mirrors would say, okay, it points directly away from this focus, so like that. This one points directly away from the focus on the opposite side also. The second ray is just the same through the point where the principal axis meets the lens, and that means the little arrow ends up right there where they appear to intersect, even though they don't really intersect, which makes that a virtual image. Where is it? Virtual image there. Also, this one got smaller, so it's reduced instead of magnified, and this image is the same orientation as it started out with, so it is upright. It did not get inverted. It did not get turned upside down. Remember, even if it starts upside down, if it ends the way it started, it did not get inverted, so it would still be upright. And this one starts and ends the same way, so it's upright. There you go. Now you've got what you need. Do the whole thing.